Okay. If you try to look at the actual deformation that is going on inside a body, for example, a two-dimensional case like this, or a plane case. Suppose we look in only in a plane XY. Okay. So in this XY plane, then you would have displacement function U representing the displacement in X direction, right? And displacement function V representing the displacement in Y direction. So if you want to say how your original length dx is elongated in X direction, how would you do that? Then you subject this dx to the displacement function u, right? Because the displacement function u would tell you how much x would displace in X direction. Okay. So if you subject dx to a displacement function u and you want to know how much dx has elongated in X direction, then you would compute this term right here. Okay. All right. So this would tell you how much dx would elongate, right, with respect to x in X direction. Okay. All right. So this is how you compute this dimensions right here. Okay. All right. So that's an example. Now, when you want to describe deformation of a structure in plane like this, then as I mentioned previously, you can't use only a single point to describe deformation. So you can say that I have a point P here, and then I can describe the deformation of a point P like that. Okay, because there's no deformation to be described. Okay, it's only a movement of the point. So in order to describe deformation, you need to have another point, please. So you need to have this point R and P and connect this line between the two. Okay, and in each direction, okay, you can have the component of this line segment in X direction as ds and dy in Y direction. Okay, and now when you track how this ds move, you can also look at how dx and dy would change, right, under the displacement function u and v. Or basically, if I think of ds as very small or going to 0, so this dx and dy become your differential side of a point P, right? So meaning that basically you are looking at a point P, but you construct a virtual side dx and dy, a differential side dx and dy, in order to try to describe the deformation of that particular point P. But it's not really a point that you're describing a virtual differential area, right? So you need a virtual differential area, dx and dy, right? So this area, okay, in order to be able to describe deformation for this point P. Okay. All right. So now that we already have our differential sides, dx and dy, we want to try to understand how this relates with the strain component or the strain quantities. For example, epsilon x. What is epsilon x if you look at dx and dy? So along this side, you would see that if you, let me erase this so you won't get confused. Okay. So this line here undergoes both u function and v function, okay, to become this line right here, okay. But as I said previously, the how much this line has elongated in x direction only would depend now on the u function, because the u function governs how you displace in x direction, right? So if you look at this component here, this component here in x direction, you would see that it's governed by this displacement function u and the derivative of u in x with respect to x only, okay? Because you're moving in x direction, okay? So it tells you how much it is elongate or contract in x direction. But what about if I want to find this particular distance here, where it tells you how much this line dx has displaced in y direction? So what displacement function should I use then? So I should use this v function, right? Because it describes how your body is displaced in y direction. But this is the displacement of the length dx, so this term becomes del v by del x dx, okay? All right. So in a way, you can see that this change of angles of this side dx is change of angles there to here, basically relates to this term right here. Okay. Now let's take a look at this side dy. Okay. So dy has become this side right here. Okay. So again, if you want to see how much dy has elongated or contracted, then you must take a look at the displacement function v, right? So displacement in y direction. So you get this term right here, okay? To tell you this magnitude or this dimension. And if you want to tell how much dy has moved in x direction, okay? So you need to use the displacement function u, right? Because displacement function u tells you the displacement in x direction. Okay. And you see that this change of angle is related with this term right here. Okay. So this is what, remember that this is what's going on at point P, right? We are trying to describe what's going on at point P, but in doing so, we can use only the location of that point, because you can't describe the information of a point. You need to have this virtual differential size dx and dy to do that. And the differential size dx and dy undergoes this displacement u and v, right, to become this side, this size, and this size. Okay. So what about these two sides then? This side and this side. Where it come from? It comes from this side because you have this side, so this side has to be parallel to this side. Okay. So this side comes naturally from this side, and this side comes naturally from this side. So it's a parallelogram that is constructed from only these two sides, right? This side and this side. Okay. So basically, you have these two vectors. Okay. And you construct this parallelogram based on these two vectors. Just as you have this differential side dx and dy, and you construct this based on these two vectors as well. Okay. Okay. Now, why is that? Because you are virtually constructing this differential length from a point. Okay. So this virtual size that comes from this point. So these are the sides that comes from these two virtual sides. So it has to be a parallelogram. Okay. All right. So now once we have all this geometry, then you can try to relate between this quantity, okay, and this quantity right here. So you can see that the difference between this and this, okay, basically gives you epsilon x, right? And also epsilon y, basically term. And now the terms theta 1 and theta 2 right here is basically this term, the summation of this term, which essentially tells you 2 times of epsilon xy, or what we call gamma xy, or our engineering shear strain. So basically, the engineering shear strain, okay, in a sense, tells you the change of angles, right, within your differential body. Okay. So if you think of okay, engineering shear strain, when you describe engineering shear strain, okay, we normally think of engineering shear strain as something like this. Okay, so this is the change of angle, right, or your engineering shear strain. So this change in angle is comparable to the summation of this theta 1 and theta 2. Okay, if you compare with this shape right here. Okay. All right. So those are the strain components. So now you can also describe, just like for the stress components, you can also describe strain components using different coordinate system as well. Okay, and by looking at different coordinate system, meaning that you are looking at this differential area as well, but you use different coordinate system to look at them. Okay. All right. Now, Ajahn, what about other components? For example, epsilon yz, or or epsilon xc. Okay, can we use this concept, this same interpretation to try to describe what's going on in those planes? The answer is yes. You can simply describe them by, you can change this to YZ plane. Okay, so if you look at the YZ plane and you change this component to dy and dc, okay, then you can use similar terms, similar derivative terms to try to describe what's going on in YZ plane, just like for the XY plane. And it would give you this epsilon YZ. So meaning that if you look in YZ plane, the change of angle in YZ plane would also give you the sense of a shear strain in Y and Z direction or in YZ component. Okay. The same for XC plane. So if you want to look at epsilon XC, you can just change this to X and Z. Okay. So the shear strain component basically tells you what the change of angle in each set of planes, basically. Okay. So change of angles in XY plane is described by gamma XY or epsilon XY. Change of angles in YZ plane is described by gamma YZ or epsilon YZ. And change of angles in XZ plane is described by gamma XZ or epsilon XZ, respectively. Okay. So those are the strain components in 3 dimensions. You should choose each plane to describe them. Okay. Now that we have the strain concept, the stress concept, equilibrium concept, or you also need the relationship between the stress and strain. Okay. So this relationship is usually referred to as the constitutive relationship. Now, the constitutive relationship meaning that you need to compute stress from strain, for example, right? So if you have your strain component, you would like to compute your stress based on your strain that you already have. Okay. So this relationship can be constructed by looking at all the independent stress and strain components. Now, in a stress matrix and a strain matrix, you have a total of nine components, right? But 6 of them are independent because the matrix is symmetry. Okay. So based on symmetry, you only have 6 independent components for stress and for strain. So you can write this relationship as this equation right here. Okay. And if you concern yourself only for isotropic material, okay. Now for isotropic materials, you can use this set of relationships to compute stress from strain and vice versa, strain from stress. Okay. Now you would see that for isotropic material, you would have this set of relationships. Okay. Now in these equations, E is the Young's modulus, right? Or the modulus of elasticity, or the relationship between stress and strain, assuming that this relationship is linear. Okay. And G, or the shear modulus, okay, is computed based on this equation right here. And this mu is the Poisson's ratio. Okay, so the Poisson's ratio is relationship between the deformation in one dimension with respect to the other dimension. Okay, so suppose you are trying to compress your material in one direction, then it try to expand in the other direction. But this Poisson's ratio would control or would tell you how much it would deform or expand in the other direction. Okay. The Poisson's ratio, the typical Poisson's ratios that we use is, for example, we use 0.3 for steel and around 0.2 for concrete. Okay, so those are the values that are normally used. Okay, so based on these equations, okay, in our course in which we would focus ourselves on only plane problems, okay, so we'll concern ourselves mostly with plane problems or what's going on inside the plane. For example, you can say an XY plane. Okay? So if you take a look only on XY plane, the relationship would come down to two different forms. The first one is called plane strain, and the other one is called plane stress. Okay. So the plane strain relationship between stress and strain is for the situation where you have no out-plane strain components. Okay, so suppose you have something that can deform only in XY plane. So it means there's no deformation whatsoever in the out-plane direction. Okay, or you can say that the displacement function is 0 in Z direction if you look at it only XY plane. Okay, so all these strain components would become 0. Okay. Now, what are the examples of this plane strain problem? If you look at something that can deform only in XY plane, only in plane, but no deformation whatsoever in the out plane direction. So meaning that it's a thin section of something, right? It's a thin section of something with constraint in out plane direction. Okay, so no W displacement in this direction is 0. So you are only allowed to expand or contract in plane only. Okay, so it's like a thin slide without no movement on the other direction, on the perpendicular direction. Okay, so what kind of structure would look something like this? Can you think of any structure that would behave this way? Let me ask Celine Porn. Celine Porn, are you there? Yes, can you think of any structure that would behave this way with no outplane displacement? อะไรนะฮะกระดาษเหรอ like a paper, a piece of paper. Okay, so you think of a piece of paper, yes. A piece of paper would have the same geometry as a plane structure, but the behavior would be entirely different, right? Because for a piece of paper, you see that it can, because it's kind of slender, so it can also have a lot of outplane displacement. But it needs to be constrained. Constrained means no movement or whatsoever in the outplane direction. So anything that is suppressed against movement its perpendicular direction. Okay, so thank you, Surinpon. If you think of, for example, a structure that is quite long, okay, it's quite long, and if you slice through a section of structure and look at that section in plane only, then you would see that because the other direction is quite long, right? So you can think of this slice that is cut through your structure as having no movement whatsoever in the perpendicular direction. For example, if you think of a dam, right? A dam. Okay, so if you have a dam. Okay. Okay, so for a dam, you have water pressure like this. Okay, and because the dam is usually long, it's usually long. Okay, so you can, if you slice a thin section, right? Slice a thin section like a slice of bread, like a piece of bread, a piece of your dam in the slice. Okay, so you can see that on this slide, you can think of it as having no movement or whatsoever in the perpendicular direction, because you know, it's constrained by the adjacent dam that is quite long, right? So it's constrained against movement in the perpendicular direction, something like that. Okay, so dam is an example. The other example would be what? Tunnels, right? Tunnels can also be thought of as a dam. Okay, so suppose you have a tunnel, okay, and this tunnel is quite long. So if you slice through a thin, if you have a thin slice of your tunnel cut out and think of it as a plane structure, then the perpendicular movement in this direction would be virtually zero, right? Because it's constrained against its movement in this direction because of its large dimension in its longitudinal direction. So tunnel can also be thought of as a plane strain problem as well. Okay. So for this kind of problems that you have, you can have the assumptions of plane strain. You can see that the relationship between your stress and strain would come down to this equation right here. So you can use this matrix form of equation to solve for your stress if you happen to know strain. Okay. Okay. Now for plane stress problem. Okay. Plane strain means strain components only in plane. Right? So plane stress would also mean stress components only in plane. So you only have stress acting in plane. So that means you would have no out plane stress component. So all these stress components in z direction would be zero. Okay. So the examples of this kind of problem would be our typical plane structural problems, right? So most structural problems are plane stress problems because, for example, you think of a plane structure, okay, and you have loading in the same plane, right? So the loading is acting in plane of the structure, and in plane structure or in plane structural analysis, you normally assume no out plane, right? No out plane behavior is going on. So you assume that all the stress components are happening in plane only. So most structural analysis problem or structural mechanics problem would fall into this category. So for plane stress problems, you would have this set of equation to describe the relationship between stress and strain. Okay. All right. So those are the constitutive relations that you can use for plane strains and plane stress problems. Okay. Now that completes the review. So let me go through your assignment a little bit. Now, before we do that, does anyone have any questions? Okay, so let me go through this our first assignment a little bit. Now, in our first assignment, this has also been uploaded in course view, so you can take a look later on. We have 5 problems. Okay, the first one gives you a displacement field. So these are displacement functions in x, in y, and in z directions. Okay, so the problem asks you to for some basic concept on how you can understand how would the displacement mapping gives you information on the deformation of a body. Now remember that when you want to describe, in this case, you want to describe a distorted configuration of a point, right? Of a point with a certain coordinates. Okay. So at that particular point, obviously you can compute what's going on for the point in terms of the displacements, right? But in showing the distorted configuration or in showing the deformed configuration, you can't just use a point to do so. Okay, so you need to construct a virtual differential size, just like what we discussed previously. So you need to think a little bit about how you can draw those distorted configuration based on the coordinates of a certain point, okay, that you are given. So that's this problem 1A. Now for problem 1B, let's determine the coordinates. So that's straightforward. And also it asks for you to compute the spin. The spin is basically a rigid body rotation of point A. So it somehow related with the rotation, okay, or change of angles of the point. And 1D asks you to find principal strains corresponding and corresponding principal directions. So the principal strain and principal directions must be computed based on the so you need to compute the strain component source, right? Okay, so you need to compute the try to solve the eigenvalue problems. Okay, that would give you the eigen pairs or the eigenvalues and the eigenvectors. The eigenvalues would give you the principal strains, and the eigenvectors would give you the principal directions of strain component. Okay. Now, in problem 2, this asks you to compute simply the direction cosine of x. Okay, so this is straightforward. Okay. And problem 3, you are asked to compute the percentage of elongation of line AB. So the percentage of elongation of line AB corresponds with the strain in that direction. Okay, so that means you must somehow be able to compute strain in this direction. So you have to uh, relate the concept of how you can describe strain in different coordinate systems and use that concept to try to solve this problem. Okay. In problem 4, you are given a certain set of stress functions and asked to verify if these equations satisfy the equilibrium equation. So we have to adopt the differential forms of equilibrium equations and try to see if you can use this information to verify that. Okay. And in our last problem, you are asked to determine the principal stresses, okay, and also determine the stress components in a different coordinate system. So that's quite straightforward. So you have any questions on this assignment problems? Now I will give you 2 weeks to complete this assignment, meaning that you have to submit the assignment to me via email. I'll give you the email address later on for submission in course view. So you should look up in announcement for the email address to submit your assignment. And the assignment is due in 2 weeks time. And I will give you the details of that also in course view. Okay. So before you are dismissed, let me ask you this about the midterm exam week, because as far as I understand, the midterm exam is scheduled between the week of March 7th, right, and March 11th. But I have heard that some of you have to take midterm exams next week. Normally during the exam week, we will have no class. So that's why I asked you that probably would you like to have no class for next week or the week on the official midterm exam? So it would be no class on either Monday, March 7th or Monday of next week. Which one would you prefer?
Next week,
Okay. So I heard one of our friends suggest that maybe next week. Anybody would like to have another suggestion? Or anyone would object to that suggestion? Okay, so if not, then we will have no class on next week then, and we will resume our normal class on the Monday of March 7th, if there's no objection from you guys. Okay. Okay then, so if there's no question, then you can leave now. Unless if anybody stays, then we can discuss a little more in Thai, if you would like. So for those of you who don't have any questions, you can leave now. นะครับสำหรับคนที่อยู่ต่อก็เผื่ออยากจะคุยเป็นภาษาไทยบ้างนะฮะไม่รู้ฟังมีปัญหาอะไรไหมที่เราเรียนกันวันนี้นะครับเผื่ออยากจะถามอะไรเป็นภาษาไทยเชิญนะครับ มีไหมครับ ไม่มีเหรอ แสดงว่าคลาสเราเก่ง
ถ้าอาจารย์ครับ
ภษ
ถ้าเกิด
ทุคน
ถ้าเกิดทำการบ้านอะไรสงสัยถามอาจารย์ทางเมลได้ใช่ไหมครับ
ได้เดี๋ยว
เหมือน
ผม
เดิม
จะให้อีเมลสำหรับการติดต่อของคอร์สนี้ไปให้นะเดี๋ยวผมจะประกาศไปในคอร์สวิว
ครับผม
คุณพยายามใช้อีเมลนั้นแล้วกันมันจะได้ไม่สับสนนะครับ
อาจารย์ครับ
ครับ ไม่มีใครงงเลยเหรอคอนเซปต์ที่คุยกันวันนี้ผมว่ามันฮะเชิญครับสวัสดีครับ ผมว่ามันดูมีเรื่องน่างงหลายเรื่องนะแต่ถ้าคุณไม่งงก็โอเคโอเคครับ ถ้าไม่มีอะไรเพิ่มเติมก็ I'll see you on Monday March 7th okay so have a nice week then
ขอบคุณมากครับ
ดีค
ขอบ
รั
คุณครับ
บ
อาจารย์
ดีครับ
Thank you อาจารย์ Have a good day อาจารย์